Try and imagine the G-force that piles up during the launch of a rocket. Incredible stresses applied to the materials it is manufactured from. Now, engineers need to know in advance that these materials they have chosen, for example, a metal alloy produced through additive manufacturing, are going to withstand the launch. But this is more complex than it sounds, and here's why. Those rocket walls won't be solid alloy. They will have structures and empty spaces within the walls, carefully designed to make it lighter. So if you're an engineer, what do you test? The metal? The structure? Or both? Let's think this through. This is ASU. Every material has properties. The ABS plastic that is used to make a Lego brick is cheap, stiff, and lightweight. The superalloy metal in the blades of our aircraft jet engines can withstand very high temperatures. Aluminum is easy to roll into very thin foil for use in our kitchens. Our ability to understand a material's properties is crucial to our ability to firstly select a particular material for a particular application, and secondly, to design the part with the correct size and shape so that material and design both work together to give us a performance we expect. This is why ABS plastic, despite its cost advantages, has not found its way into jet engine blades. Nor are we likely to see titanium foil lining our oven pans. There exists a class of materials, however, that are in a gray area between this separation of material and design. We call these materials by many names, such as cellular, architected, or meta materials. A great natural example of this is the bone in our bodies. Each bone has a different shape and size, adapted for its function and position in the body. But that's not all. Peer inside of bone, and you notice that it is not a solid chunk of material shaped to a particular form like a marble sculpture. Instead, bone consists of tiny, curved structures fused to each other with empty space surrounding them. It is this empty, cell-like structure that makes us say that bone is cellular in nature. Engineers have been inspired by natural structures like bone, wasp and honeybee nests, and deer antlers to develop similar cellular materials like honeycomb panels that we use in aircraft, or packaging foam used in shipping goods around the world. In all these cases, it's not just the material itself, but also its structure that influences its behavior. And this is where it gets interesting. Search for the properties of ABS plastic online, and you will find datasheets that will tell you ABS's modulus, density, and a host of other properties. But what is the property of an aluminum honeycomb panel? What are the properties of bone? Of a 3D printed lattice made of ABS? This is harder to determine since it depends on the geometry of the cells that constitute the structure. And this is where homogenization comes to the rescue. Homogenization asks you to imagine that both the material and the empty space around it are in reality just one material, but with different properties. We call these properties effective properties, since they are strictly speaking not true material properties which are valid at every single point. With a cellular material, depending on where you interrogate, you get a different property. The idea of homogenization is not limited to cellular materials. A class of materials called composites, where two or more constituents are combined into one, also benefits from this approach. In carbon fiber reinforced composites, for example, the carbon fiber is an aspect of the material that is separate from the matrix it is embedded in. The properties of the composite depend on the relative amounts of the different materials and how they are positioned relative to each other. Now, effective properties are more challenging to determine experimentally since they are fundamentally dependent on the geometry being tested. Additionally, they are also highly dependent on the direction you test them in. Once determined, however, they are critical for designers and engineers who build structures out of them. As we venture across the solar system, the details of material strength are crucial. Understanding homogenization and effective properties of materials is a critical aspect of manufacturing. The products we make must be strong in the ways we expect them to be. They must behave how we want them to behave. When you are 100 million miles from home, being able to rely on your equipment really matters. This was ASU. Thanks for watching.